Hello everyone, so today I'll be discussing question number 35 of GATE 2008. The spans to be loaded uniformly for maximum positive upward reaction at support P as shown in the figure below is or are. So is a structure, we need to tell which span we should load so that we get maximum positive upward reaction at support P. This we can tell easily if we would know the ILD for support reaction at P. So 4 options are given to us. Either we should load span PQ only, PQ and QR, QR and RS, or PQ and RS. So out of these 4 options, we need to tell which span we should load so that we get maximum upward reaction at support P. Now let us start with the solution of this question. I have already said if we would know what is the ILD for support reaction at P, we can easily find out which span to be loaded. So before diving into the final solution, let us discuss what is an influence line diagram. An influence line diagram represents the variation of either reaction, shear force, moments at a specified point in a member as the concentrated unit force moves over the member. Okay, so for when we draw the bending moment diagram, we draw the bending moment diagram for fixed loading. Therefore, the bending moment diagram actually represents the effect of fixed loading at all the points, while the influence line diagram represents the effect of moving load at a point. So for bending moment diagram, the loading is fixed, the location of loading is fixed, while for influence line diagram, the loading is moving. We are moving the concentrated unit force, and we are studying its effect on a specified point. So that is a basic difference between bending moment diagram and influence line diagram. For our problem, we need to tell the loading is not fixed. For our problem, we need to tell where we have to place the loading so that we get maximum positive upward reaction at point P. Therefore, for this problem, we need to draw the influence line diagram for support reaction at P. So there are 2 important points. ILD is a straight line for statically determinate structures. So we should keep these 2 points in mind, that ILD is always a straight line for statically determinate structures, while ILD is curved line for statically indeterminate structures. So these 2 points we have to keep in mind. There's a conventional method to draw the influence line diagram, but for this question I'm going to discuss a very quick method which will be helpful for GATE exam. The method is drawing the influence line diagram using Muller-Breslau principle. We'll see how to use this method for drawing ILD for reaction, shear force, and for bending moment. First, I'm going to discuss this method for statically determinate beam, and then we'll move towards to statically indeterminate structures. For drawing ILD for support reactions, let's call it as A and this support as B. So the first step is remove the vertical restraint for that particular point. Suppose we need to draw ILD for reaction at A, so the first step will be removing the vertical restraint at support A. So we'll remove this vertical restraint. So we have removed the vertical restraint for this second case, and the B point will remain same. The second step is apply a unit displacement at that support. So we'll apply unit displacement. We will push this point upward by unit amount. So this will be 1. So whatever be the deflected shape of the beam will be the ILD for support reaction RA. Similarly, if we need to draw the ILD for support reaction at B, we will follow the similar step. The first step will be we will remove the support vertical restraint at support B. So we have removed the vertical restraint at support B. Support A is still restrained. The second step is push this point or displace the point B by unit amount. So we have displaced it by unit amount. So whatever is the deflected shape of the beam we are getting will be the ILD for support reaction at B. So we will get the deflected shape like this. So this is the ILD for support reaction B. Now let's see how to find the ILD for shear force at particular point. Suppose we need to find ILD for shear force at point C. The first step will be, we will release the shear at that particular point. Here the point is C, by introducing a slider. So we will introduce a slider here which can move freely in vertical direction. The second step is, we will apply unit load in this particular direction. We will apply upward load in the right direction, and we will apply downward load in, or we will displace it in downward direction on the left side. Then whatever be the deflected shape of the beam after applying this displacements will be the ILD for shear force at point C. Let's see after introducing these displacement how the left and the right side of the beam will deflect. So still the point A is restrained, point B is restrained. Let's see how the right side, that is the CB section, is displacing. So when we apply this displacement here, this part will be deflected like this, while this left section is displaced downwards, so it will displace like this. So this is the deflected shape of the beam after applying the displacements. Now what is the value of these displacements? Let's call it as X. Now here the total displacement is 1. We are applying total unit displacement, so total displacement should be 1. So this lower part will be 1 minus X. We can easily find out the value of X here by this X divided by this length. This length is 7.5 here. So X divided by 7.5 equal to 1 minus X divided by this length, which is 2.5. It's 2.5. It's 3 times. So X equal to 3 minus 3X. 4X equal to 3, and X will be equal to 0.75. So we get the value of X as 0.75. Therefore this lower part will be 1 minus 0.75, that is 0.25. So using this method we get to know the shape of the ILD as well as the values. So this is how we will draw the ILD for shear force at a particular point. Let's see now how to make the ILD for bending moment at a particular point. So suppose this is point D and we need to find the ILD for bending moment at point D. So the first step is, we will release the moment at point D by introducing an internal hinge. So we have introduced an internal hinge. So the point D, the both sides are free to move now, rotate now. The second step is, we will apply unit moment like this. So whatever will be the deflected shape of the beam after following these two steps will be the ILD for bending moment at point D. So after applying the moment at this hinge, the beam will deflect something like this. Let's call this angle as theta 1 and this angle as theta 2. So it has rotated in this manner now. So theta 1, the condition should be theta 1, total rotation should be unit. So theta 1 plus theta 2 should be equal to 1. So theta 1 is, let's call this point, this length as X. So theta 1 is roughly X divided by 5, and theta 2 will also be X divided by 5 equal to 1. So from this we get 2x divided by 5 equal to 1, and x should be equal to 2.5. So this is the value of x we are getting. So this is the ILD for bending moment at point D. We are done with statically determinate structures now. Now we'll see how to draw ILD for reaction, shear force and bending moment for statically indeterminate structures. The steps are similar. The only difference is for statically indeterminate structures, the ILD will be curved lines, while for statically determinate structure it was straight line. So the first step for drawing ILD for support reaction A, let's say, is removing the vertical restraint at point A. So we will remove this vertical restraint. The second step is applying unit load at the support location, and so we will apply a unit displacement. So we'll displace it by unit amount at this point. So we have displaced it. So after displacing this point A upward, it was here, let's call it as A dash. So after displacing it to A dash, whatever will be the deflected shape of the beam will represents the ILD for support reaction at A to some scale. Now let's see what is the deflected shape of the beam now. So the deflected shape of the beam will roughly be the beam will deflect roughly in this manner. So for statically determinate beam, we could find the values at different points. Suppose here we could find the value of x using the geometry. Here also we could find the value of x. But in this case, for finding out the exact values at different points, we need to do some more calculations. But here I'm going to just stick with the shape of the ILD, because for our problem we just need to know what is the shape of the ILD so that we could determine which span to be loaded to get maximum upward reaction at that support A. So this is the ILD for reaction at A, which is for a statically indeterminate beam. Let's see how to find the ILD for shear force. So here also suppose we need to find ILD for shear force at point D. So we will introduce a slider at this point. Like before, we will apply the load upward displacement on the right side and downward displacement on the left side. So whatever be the deflected shape of the beam roughly will represents the ILD for this particular beam, ILD for shear force at point D. So this, after applying this displacement, this kind of displacement, the beam will roughly deflect like this. This will be the deflected shape of the beam. So hence this will be the ILD for shear force at D. See, the steps are similar. It's just that for statically indeterminate beam we are getting curved lines. Let's see for the bending moment now. Suppose we need to find the ILD for bending moment at point D. The first step is we will introduce an internal hinge here. Second step is we will apply this unit moment here like this. So let's see what is the deflected shape. So the deflected shape of the beam will be like this, because this part is restrained, this part is restrained and this part is restrained. So the deflected shape will be roughly this. So this will represents the ILD for bending moment at point D to some scale. After discussing the Muller-Breslau principle for drawing influence line diagram both for statically indeterminate beam and determinate beam, we will come to our final solution. So here we needed to find which span we should load so that we can get maximum upward reaction at point P. So for this we will draw ILD for support reaction P. So for drawing ILD for support reaction P, the first step is remove the vertical restraint from point P. So we will remove this restraint, and the second step is we will apply unit displacement at point P. So we will apply the unit displacement like this. So whatever be the deflected shape of the beam will represents ILD to some scale. So roughly the deflected shape will be like this. Since it is restrained at this point, this point, this point, so this deflected shape will be like this. Now we know the ILD for support reaction at P to some scale. So from this shape of ILD we can see that if we will load this span PQ and span RS, because they are having positive values, positive, negative and positive, then we will get maximum positive upward reaction at point P. Therefore our final answer will be option number D, that is PQ and RS. So if we will load span PQ and RS, we will get maximum upward reaction at support P.